Okay, it's time to do some solving with exponential and log equations. So up until this point, we've learned a little bit about exponentials and logs from a graphical perspective. We understand some key properties. So now we're going to look at solving. And as we dive in, I'm just going to throw a bunch of examples your way to help you see how different all of these solving problems can feel. And maybe before I dive in, I'll just kind of share a couple big picture tips, I guess you could say. Um, so sometimes when we're solving, we can use making the bases match as a technique. So I'll start out with that technique. Um, Sometimes we need to use log properties, and this will include things like the product, quotient, and power properties. Sometimes we need to use our way of rewriting exponential form into log form, or vice versa. Probably the vice versa is actually more useful. So, or log form into exponential. So those are just a couple ideas. And I think a good way to kind of go about learning this is just to stumble upon these different ideas as we need them. So those are just a couple thoughts. If you'd like, we can surely come back to this list and add on as we go through some examples. So we'll see if this turns into multiple videos, but let's just dive in with a couple examples. So let's start more along the lines of exponential. And I want to pick on something that's going to make us think about making the bases match. So let's say we were given 125 to the power of 2x multiplied by 125 to the power of just 1x set equal to 25 to the power of 2x minus 1. So I'm giving us something kind of crazy right out the gates. I think in previous algebra classes, you've likely solved more simple exponential equations. So we're kind of ramping it up fairly quickly here. So when I say, can we make the bases match, I look at my bases currently in this problem and I see a 125, a 125, and a 25. Those are all decent sized numbers. So we want to think about shrinking them down to a smaller base. So 125 and 25 both have a base of 5 in common, right? So 125 is the same as 5 cubed, so I can rewrite 125 to the 2x as 5 cubed to the 2x. I can do the same exact thing with the next 125, rewrite that as 5 cubed, and then finish off raising it to the power of x. And then on the right-hand side, 25, of course, that would be 5 squared, right? So we can rewrite this 25 on the right-hand side as 5 squared, and it's still being raised to the power of 2x minus 1. So before too long here, we'll be at a spot where we have 5 to a power equals 5 to a power, and that's a really good spot to be in because then you can simply set those powers equal. Let's keep simplifying a tad bit more. This will refresh us on rules of exponents. When I have a power raised to a power, we multiply. So this first piece cleans up to 5 to the power of 6x. The second piece cleans up to 5 to the power of 3x. So I just multiplied those powers there. On the right-hand side, same story, just be a little careful to distribute. So I'm multiplying these powers, which really means 2 times 2x minus 1. So there I'm going to get a 4x minus 2 when I distribute carefully. So we're looking pretty good. On the left-hand side, I'd like to take one additional step, and that is if I'm multiplying and my bases are the same, we know from our prior experience that we can simply add the powers. So 6x plus 3x gives us 9x. So this is one route to go through solving this problem, right? Maybe you saw something different, so in that case, go for it. I'm just throwing kind of the matching base technique at this problem. So now that our bases match, we will go ahead and set the exponents equal, and then we'll solve what remains. So we'll set the exponents equal. So that's going to give us a linear equation. We're going to have 9x is equal to 4x minus 2 once we snag the exponent on the left and set it equal to the exponent on the right. So let's just finish solving this linear equation. I'll go ahead and move all my x's to the left, giving us 5x equals -2. Divide by 5, and we're going to sneak in our solution right here. Looks like we're getting x as -2/5. Okay, so that would be the solution to the given exponential equation. You are sure welcome to plug that in and check your work. I'll leave it to you guys for those of you who like to check. It's always a good idea. Another fun technique I know we've been talking about is you can always graph the left and right side of the equation, and we're looking for the x value where they intersect. So that's another way to check. Lots of possibilities. I'm going to do another one that has the same kind of feel, but it incorporates some fractions. So this was a pretty friendly making the bases match kind of problem. You may disagree a little bit because the numbers are large, but this next one will incorporate some fractions. All right, so let's try another one similar to that guy. This time, let's say we were given 64 divided by 1 over, I'm going to go with some crazy numbers here, 256 raised to the power of -x minus 2, and that's equal to 4 cubed. All right, so again, we're solving. We're looking for the value of x that makes this statement true. And like always, if you have a knee-jerk reaction, roll with it. There are many ways you can go about simplifying and solving this one. So I would love for you guys to take the initiative and try something, get your solution, and then you can always zip forward and compare your solution to mine if you'd like. I'll walk through a couple ideas that might not be the most efficient, but maybe would be the most intuitive. I'd like to start by talking about this denominator piece, which is kind of messy. So let's drag him out over to the side for just a second and talk through that. If I have 1 over 256 raised to the power of -x minus 2, well, for one thing, I am still geared towards making my bases match, so I'm going to try to rewrite that 256 using a smaller base, and I use this smaller base of 4 as a hint on the right-hand side. So if you stop and think about it for a moment, let's see, 4 squared is 16, 4 cubed is 64. Okay, so that's good, we see that number. And then if you take 64 and times that by 4, we should get back 256. So I'm going to rewrite the 256 as 4 to the 4th. Again, this is just a starting point here, having a couple thoughts. And that 4 to the 4th is in the denominator, right? So I can actually yank it up to the numerator as long as I make the exponent negative. So when I move this piece from the denominator up, the exponent becomes negative. And now we're in a spot similar to what we saw in the last example where we've got a base to a power to a power. And so what we need to do is multiply the powers. So I'm going to get here 4 to the power of 4x plus 8, because when we multiply the powers are -4 times -x minus 2. So if we use our distributive property there, we get a positive 4x and a positive 8. So I don't know about you guys, but that last line of 4 to the power of 4x plus 8, that feels a lot nicer to me than the mess we began with in the denominator. So I just chose to kind of tackle that piece a bit first on the side so that I can put it back into the problem that way. Okay, how's that seem so far? Hopefully you're tracking with me and feeling all right. Okay, so let's go back to the original problem now. Kind of as a result of simplifying that denominator, we notice that 64 is the same as 4 cubed. Sorry about that. And then the denominator, stealing all of our side work, was equal to 4 to the power of 4x plus 8. And on the right-hand side, it was just equal to 4 cubed. So, couple options here. Some of you may be fans of cross multiplying, right? That's always a fun strategy. Some others of you may notice that, hey, the numerators of these two fractions are the same, therefore the denominators might be equal. So how about we take that approach here? What if we just say 4 to the 4x plus 8 must equal to 1, because these 4 cubed terms in the numerator were the same. So it's not always going to happen this way, but when you can, take advantage of it. And let's see if that makes this feel a little easier to solve. You're probably thinking, as I am right now, that 4 and 1 are not the same base, but in math we can always strategically rewrite 1 as something to the power of 0. So I thoughtfully choose 4 as the base, right, because that's the base that's desired here. And would you all agree that 4 to the 0 is a fair rewrite of that right-hand side, which was just 1? Now, at this point, I can say the same thing we did in the last problem, which is, hey, the bases match, therefore, we can set the exponents equal and solve. So with the route that we're taking here, which again may look very different from your route, probably even looks different from my route if you ask me to do the problem tomorrow, would be to set 4x plus 8, which is the power on the left, equal to 0, which is the power on the right. Solving that guy, it looks like we could subtract 8 from both sides, divide both sides by 4, so we get back a solution of x equals -2, which again, you are more than welcome to check by plugging into the original, make sure it makes a true statement. Those of you who prefer graphing, graph the left side, right side, and find that they intersect at x equals -2. Cool. Okay, so those first two examples, again, fairly similar. I promised to show a little bit more of the variety of solving, so let's keep diving into other types of solving problems. What if we were asked to solve an equation such as 8e to the power of 5x minus 2 is equal to 10? This has a very different feel to it. It's still exponential. We have a base of e, which we haven't seen yet in this video, but put on just your prior algebra knowledge for a moment and think about, how do you isolate x, right? Solving is, as we've always heard, isolate x. So I think you guys would agree an intuitive first step is just to move 2 to the other side to work on getting x alone. So we have 8e to the 5x equal to just, let's see, 12. We still want to keep getting x alone, so how about now we divide both sides by 8. And we'll reduce that fraction on the right-hand side, so that gives us e to the 5x on the left. 12/8 we could reduce to, what would that be? Oops, 3/2. We divide top and bottom by 4. Okay. And now we're in a spot where we have an e and we don't want an e, so this is going to feel a little different. Remember our knowledge about inverse functions and how they strategically undo each other, right? So if I had an x squared equals 9 equation, we would just rope in the inverse function of square root, and that would finish solving it for us. We're in a very similar spot here, although it feels different because it's exponential. So the inverse of e is log base e. And log base e, remember, is our natural log function, so ln. So what we're able to do here is introduce the ln on both sides pretty much in the same way that in this x squared equals 9 equation that I just brought up a moment ago. Remember how we would have square rooted both sides? So similarly, in this problem, I'm going to introduce ln on both sides. So it's basically like we're composing both sides with the ln. So ln of the left is equal to ln of the right. We strategically introduced the natural log function so that on the left, the ln and e functions as inverses cancel out, leaving just the argument. So if you think back to Unit 1, remember how we learned that f of f inverse of x is just x? or f inverse of f is just x. That's what's happening here. So the ln and the e as inverse functions cancel out, leaving us just with the argument, which in this case is that power of 5x. On the right-hand side, don't worry, it's just ln of 3/2. That is a decimal. We could use a calculator, but let's just solve this guy exactly. Let's not even worry about finding a decimal. Let's just find the exact solution. So we are so close. If you tracked with me through that ln piece, all we got to do is divide both sides by 5. And an exact solution will be x equals the natural log of 3/2 divided by 5. And in your homework, you'll see some questions, some problems where it says find an exact solution. So this is what we mean by an exact solution. It is just a number, right? ln of 3/2 is a number divided by 5 is another number. So I'm not requiring you to punch it in a calculator and get a decimal. So we will go ahead and leave that one there. Cool. Well, let's do one more in this video, and then you'll probably feel pretty stuffed in terms of solving with logs and exponentials. As I said, each of these have a slightly different feel to them, so I'm going to hold true to that with this last example, make it feel different from the ones we've seen so far. Let's say that we're asked to solve again. Our solution this time will be exact, but let's say we've got 6 to the power of 2x plus 1 set equal to 11 to the power of x minus 3. Okay, so I chose this example because the base of 6 on the left and the base of 11 on the right can't be rewritten in terms of smaller bases, right? It's not like a number such as 64 or 16 where it can be written as 4 cubed or 4 squared. So we aren't able to use the make the bases match strategy, which is kind of a bummer. But the good news is we have our log properties. So I'm going to go ahead and do a very similar thing to the last problem, and then it will have a different feel from there. I'm going to introduce a log to both sides of the equation. Algebraically, as long as we're doing it to both sides, no trouble. And at this point, I can introduce log of whatever base I want. So I could just write a log without a base on both sides. You would assume it to be a log base 10. I could have just as readily thrown an ln to both sides. Maybe I'll stick with ln. It's 2 letters instead of 3, so I'll just be a little lazy. So I'm going to do the natural log of both sides of this equation. And again, algebraically, we haven't broken any rules because we're doing the same thing to both sides. Okay. So why would we ever want to introduce a log to both sides? Well, once you have a log on both sides, now you guys are going to recognize that we can use that power property that we talked about. We haven't mentioned it yet in this video. We haven't had a need for it, but we learned about a property that says if you have log of an argument to a power, the power property lets us simply pull the exponent down out front as a multiple of the log. And this will be a perfect time to use that. So I'm going to get 2x plus 1 on the left times the natural log of 6 set equal to the power on the right, which is x minus 3 times the natural log of 11. So that's what it looks like in this instance to use the power property. From here, it's going to be an algebra dance, so hang on. What I'd like to do, again, you have some options, but probably what I would encourage you to do is to just distribute the ln terms on both sides to the parentheses. So it looks like we need a little bit of distribution. That'll give me 2x ln 6 plus 1 times ln 6 on the left side. On the right, it will give me x ln of 11 minus 3 ln of 11. And in some ways that maybe made the equation feel a little bit more complicated, but keep your eyes on the x terms, right? We're just trying to get all the terms with x on the same side. So what I'll do next, and I'll draw some arrows, is I'm going to move all my x terms to the left. which means I'm going to send this ln6 term, which doesn't have any x's, I'm going to send it over to the right side. And I'll pull this x ln11 term over to the left side. So this 2x ln6 term is untouched. I'm going to move the x ln11 term to the left by subtraction. The negative 3 ln of 11 term that was already on the right side hasn't moved, and then it gains a negative ln6 term from moving over by subtraction. So I just moved 2 terms in that one step. Feel free to do it step by step or whatever's comfortable. But now, again, keeping our eyes on the x that we're trying to solve for, x is now a common factor of the left-hand side. So if I factor an x out, I have 2 natural log of 6 minus natural log of 11 equal to the same exact right-hand side. And if our goal is to get x alone, I think you guys see this last step will be just divide by everything that x is being times by. So I'm simply going to divide both sides by 2 ln 6 minus ln of 11. That frees up x on the left, it's all alone. On the right, we have definitely an exact answer. We could use some log properties to try to compress it if we wanted to, but there's not really a need. If the problem says find an exact solution, well, we have definitely followed through on that. This is an exact solution. If you wanted to punch this in your calculator and get a decimal approximation, that would be easier for checking for sure. But an exact solution can involve logs of quantities that aren't evaluated in a calculator. So I hope this is a good intro to solving. I am going to do another video because I'd like to do at least 3 more just to continue showing you how diverse the exponential and log solving can be. But I hope you also feel that it pulls on your prior algebra knowledge combined with our newer knowledge of log properties. So stay tuned for that next video.